Select the major product of the following reaction. So we are given a ketone as a starting material. And MCPBA you might recognize from the alkene chapter. We use it to take alkenes and make epoxides. So this is a peroxy acid. And now we don't have an alkene, so it must be doing something else in this reaction. So peroxy acids have this general structure, right? If it's MCPBA, that is metachloroperoxybenzoic acid. But all of your peroxy acids are going to function essentially the same way. So what this reaction is with an aldehyde or a ketone, this is known as a Baeyer-Villiger oxidation. And what it's essentially going to do is it's going to insert an oxygen between the carbonyl carbon and something that's attached to it. So either between here and here or between here and here. So if we're inserting an oxygen and we started with a 5-membered ring, we're going to be making a 6-membered ring. So it's definitely going to be either A or D. So we just need to know how to distinguish between those. So if you take a ketone, so I'll give you the quick rule and then show you the mechanism. With MCPBA, you will get the ester. And so the rule is with a ketone that you're going to insert the oxygen on the more substituted side. So if we're looking at either side of this ketone, and we're not going to consider the bond to the carbonyl, we're going to look at other bonds to carbon. So we would say that this is primary and this side is tertiary. So expect our oxygen to insert between this bond, which would give us as a product then this ester. Right, so there's the ester, and I flipped it around, sorry, just automatically drawing that form of an ester, but I want to make sure that tertiary carbon is right by the oxygen. And so if you flip it over, it probably looks a little bit better and more like what we started with. So you can see that the answer is A, but let's take a look at the mechanism to see why. And now, as I mentioned in class, you are not responsible for knowing this mechanism, but I do want to show it to you to give you a bit of an idea of what's going on. So I'm going to use the conjugate base of the acid, and I'm just going to draw a generic ketone. Okay. And so if we have the conjugate base, I'm going to make the O minus. So this can attack the ketone, and this attack should look familiar. We're very used to doing nucleophilic attacks on carbonyls. So it's going to attack, and we're going to break the pi bond to get a tetrahedral intermediate. So here is our tetrahedral intermediate. So you're probably looking at this going, how on earth does this insert an oxygen? So what happens is it's really interesting, but something you'd probably have to memorize, which is why I'm not holding you accountable for it. So if we're forming an ester, this right here is the oxygen that's being inserted. So here's how it's going to happen. So you're going to have these pi electrons come in to form a carbonyl, and then one of these bonds is going to shift, or what we call migrate. Okay, and then we break this bond. So we're essentially forming the carboxylic acid is what the peroxy acid is being turned into. Well, that makes sense, right? Because if we're adding oxygen, that's an oxidation. So we're oxidizing the ketone. Something needs to be reduced. So the reduction is occurring to the peroxy acid. So this is how we get an ester. So this R group, the one I didn't put a prime on, we're shifting it, so I'm showing that being attached to the oxygen. So that's how we get our ester. And we get the carboxylate from your peroxy acids. That's eventually going to be your carboxylic acid. Okay, so we said that with a ketone that your oxygen is going to insert on the more substituted side. I'm going to give you a general rule for the aldehyde. And this might surprise you. So for with an aldehyde, if you treat this with MCPBA, you're going to get a carboxylic acid. And that's because if you had a hydrogen on this carbonyl, the hydrogen is more likely to what we call migrate. So here is the trend for migratory groups. So what's more likely to move? So migratory aptitude. So what we will see is that hydrogen moves the fastest. Okay, but then after that, it seems to be the more electron-rich groups that tend to move faster, and that's why we see the substitution on the more substituted side. So after hydrogen, tertiary alkyl groups tend to move, and then secondary alkyl and phenyl rings are about the same. So if you had a secondary side and a benzene ring on the other side, you wouldn't get good selectivity, so that would not be a very useful reaction. And then finally, that migrates faster than a primary carbon, which migrates faster than a methyl group. Okay, so we have our general rules here. So with an aldehyde, the oxygen inserts between the carbonyl and the hydrogen. Right, so with an aldehyde, it's easy. That's your fastest to migrate. You're going to definitely make the carboxylic acid. With a ketone, it's going to insert on the more substituted side. And now we have a hint of an idea why.